Welcome back to my YouTube channel. Today we will discuss intermediate value theorems. Okay. Intermediate value theorem say that any real continuous function or a closed interval a comma b to r such that f of a and f of b are opposite sign, then there exists a point belongs to open interval ab such that f of c equal to 0. That is, there exists a root between this interval ab of the function f. Okay, if function is continuous and the interval is closed interval ab. Okay, closed and bounded. Okay, that is graphically we mean that is my x-axis and this is my y-axis. Okay, suppose my a here and b here. Okay, suppose f of a, value of f of a here, function value f of a here, negative value. Okay, f of a, and f of b here, function value. The corresponding point of this point, this is b comma f of b. Okay, and this corresponding point here, this is a comma f of a. Okay, so this is a continuous function. Okay, that is this function graph of the function here to this point, joining, when joining this cut the x-axis, must cut the x-axis. Okay, this is x-axis. So this point is c here. Okay, this point. So this value is f of c is equal to 0. Okay, this idea in mathematical term is called intermediate value theorems. Okay, let's start the proof. We define a set S equal to those point x belongs to closed interval a comma b such that f of y less than equal to 0 for closed interval a comma x. Okay, that is, here we choose this point, those of point x in which this interval a comma closed interval a comma x, the graph of the function below the x-axis. Either we choose those of point in which the interval closed interval a comma x such that the function value is less than equal to 0. Okay, now given f is a continuous function. Okay, by definition of continuity of f, given any epsilon greater than 0, there exists a del greater than 0 such that x belongs to open a closed interval a comma a plus del. This implies f of x minus f of a less than epsilon. Okay, by definitions of the continuous function at a point a. Okay, at a point a. Okay, this is a definition. Okay, now so this implies f of a minus epsilon less than f of x less than f of a plus epsilon. Okay, from here now we choose epsilon equal to minus f of a by 2. Here we choose minus f of a. Why? Because f of a is less than equal to 0. Okay, this is negative point, a negative value. So we multiplying by minus, this is greater than equal to 0. So we choose epsilon equal to this. Okay. Now this equal to, from here, this equal to 3 f of a by 2. Okay. Greater than f of x less than f of a by 2. Okay, minus okay, f of a by 2. Okay, so this implies f of x less than f of a by 2, and this f of a is also less than equal to 0, so this quantity less than equal to 0. Okay, so for all x belongs to a comma a plus del. Okay, here open. Okay, this, so this equal to f of x strictly less than 0 or less than equal to 0. Now for all x belongs to a comma a plus del. Okay, so now a plus del by 4, this point also belongs to a comma a plus del. Okay, so this implies f of a plus del by 4 is less than equal to 0. Okay, so this implies f of y less than equal to 0 for all y belongs to a comma a plus del by 4. Okay, so this is a definition of S. From we defined S as follows: this the set of all points x such that this condition hold. So here this point a plus del by 4 belongs to S. Okay, this is belongs to S. So this implies a plus del by 4. Okay, so or also this set is a subset of a comma b. This closed interval is bounded. This implies S is bounded. Okay, so supremum of x is exist because S is bounded. So suppose C equal to sup of S. Okay, a plus del by 4 greater than equal to C less than equal to B. Okay, because C is a supremum and this point belongs to S. Okay, now that is, so hence A less than a plus del by 4 less than equal to C less than equal to B. So this implies C belongs to open interval A and close B. Okay, we claim C belongs to S and f of C is equal to 0. Suppose if f of C not equal to 0, So either f of c greater than 0 or f of c less than 0. Only two cases are possible. Now suppose first case, suppose if f of c greater than 0. We know that any continuous function is greater than 0 at a point c. So we can find an neighborhood around c. Okay, which function value is greater than 0 for every point belongs to this interval. Okay, that means suppose f is a continuous function. Okay, here my c, the value of f of c is greater than 0. That is here, f of c greater than 0 here. So we can find a neighborhood of c, such that all the point value is greater than 0 here. Okay, that is that. Okay, so there exists a del greater than 0 such that f of x greater than 0 for all x belongs to c minus del comma c plus del intersection a comma b. Okay, so this is called equation number 1. Okay, now here c is supremum of s, already given, already we let c is an supremum of s. So c minus del is not an upper bound, is not an upper bound of s. Okay, so there exists a point x belongs to s such that c minus del less than x, strictly less than x. Okay, or also x belongs to s. So definitions of s, by definition of s, f of y less than equal to 0 for all x belongs to a comma x. Okay, and from 1 f of x greater than 0 for all x belongs to c minus del comma c plus del intersection a comma b. So that consider the interval c minus del comma x. Okay, so consider this interval f of t value here from this is called 2 equation, this is called 2 and this is 3. It's called 2 and this is 3. Okay, now consider this interval c minus del comma x. Okay, from 1 for all t belongs to c minus del comma x, f of t less than equal to 0. Sorry, from 2. Okay, and from from 3 for all t belongs to close interval c minus tail comma x. Okay, close interval c minus tail comma x, f of t strictly greater than 0, which is a contradiction, okay, because in the same point the value of t either greater than 0 or less than 0. Both value is not possible at the same time. Okay, so in this case we have f of c is equal to 0. Okay, now second case 2. Suppose f of c less than 0. Okay, again by the property of the continuous function we can find there exists a del greater than 0 such that f of x strictly less than 0 for all x belongs to c minus del comma c plus del intersection a comma b. Okay, and again by the upper bound property c minus del is not an upper bound, so there exists a x belongs to s such that c minus del less than x. Okay, c minus del less than x, strictly less than x. Okay, now this is called it equation number 4. Okay, since x belongs to s, okay, by definition of s f of y less than equal to 0 for all x belongs to a comma x close interval. Okay, by simply by definition of x from here. Okay, and also from equation number 4, this f of x less than 0 for all x belongs to c minus del comma c plus del intersection a comma b. Okay, here c plus del by 5 or 4 any 3 belongs to c minus del comma c plus del intersection a comma b. Okay, so from this inequality and this inequality, consider the interval a comma c plus del by 5. Okay, for all values of this interval the function value less than equal to 0. So f of t less than equal to 0 for all t belongs to a comma c plus del by 5. Okay, from this and this. Okay, so by again definition of S, C plus del by 5 belongs to S by definition of S. Okay, which is a contradiction. Why? C is a supremum of S. Okay. So therefore, f of c is equal to 0, and hence the proof. In the both case, f of c is equal to 0. Okay, hence the proof.